What is the universe made of? This question has intrigued and puzzled humanity for as long as we have gazed up at the night sky. This question has captivated humanity for millennia. From the earliest civilizations to the modern era, the quest to understand the cosmos has driven our curiosity and inspired countless generations. Ancient philosophers pondered the elements: earth, air, fire, and water. They believed these were the fundamental components of all matter, a theory that shaped early scientific thought. Modern science delves deeper, revealing atoms, protons, neutrons, and electrons. These discoveries marked significant milestones in our understanding of the material world. But the quest for the universe's fundamental building blocks continues. Scientists now explore realms far beyond the atom, venturing into the subatomic world. Could there be something even smaller, even more fundamental, underlying the reality we observe? This question drives the cutting-edge research in particle physics. String theory offers a compelling and elegant answer. It suggests that the universe's most basic constituents are not point-like particles, but rather tiny, vibrating strings of energy. It proposes that the universe's most basic constituents are not point-like particles, but rather tiny, vibrating strings of energy. These strings, though incredibly small, hold the key to understanding the fabric of reality. Like the strings of a violin producing different musical notes, these strings vibrate at different frequencies, giving rise to the diverse particles and forces that make up our universe. Each vibration pattern corresponds to a different particle, much like different notes on a musical scale. This radical idea, if proven true, would revolutionize our understanding of the cosmos. It would unify the seemingly disparate forces of nature into a single coherent framework. It would provide a unified framework for explaining all of nature's forces and particles, a theory of everything that has eluded physicists for centuries. This quest for a unified theory has been the holy grail of physics, pursued by the greatest minds in history. String theory represents a profound shift in our conception of the universe, offering a glimpse into the hidden elegance and simplicity that may underlie the apparent complexity of the world around us. It challenges us to rethink our understanding of space, time, and matter, and to embrace the possibility that the universe is far more interconnected and harmonious than we ever imagined. For centuries, physicists have sought a single, elegant theory that can explain the workings of the universe at its most fundamental level. This quest has been a driving force behind many of the most significant scientific discoveries and advancements throughout history. This elusive goal, often referred to as a theory of everything, has driven countless scientific inquiries and breakthroughs. The idea is to find a unified framework that can seamlessly integrate all the fundamental forces of nature and the particles that make up the universe. String theory has emerged as a leading contender for this grand unification, promising to reconcile the two pillars of modern physics, quantum mechanics and general relativity. It suggests that the fundamental particles we observe are not point-like dots, but rather tiny, vibrating strings. Quantum mechanics governs the realm of the very small, describing the behavior of atoms, subatomic particles, and the forces that govern them. It has been remarkably successful in explaining phenomena at microscopic scales, leading to technologies like semiconductors and MRI machines. General relativity, on the other hand, describes the universe on the largest scales, explaining the force of gravity and the behavior of stars, galaxies, and the universe as a whole. Einstein's theory has passed every experimental test to date, from the bending of light by gravity to the expansion of the universe. These two theories have been incredibly successful in their respective domains. Quantum mechanics excels in the microscopic world, while general relativity shines in the macroscopic cosmos. However, they seem fundamentally incompatible when applied to extreme environments where both gravity and quantum effects are significant, such as black holes or the very early universe. In these realms, the equations of general relativity break down, and quantum mechanics alone cannot provide a complete picture. String theory offers a potential resolution to this conflict, providing a framework where both quantum mechanics and general relativity can coexist harmoniously. By proposing that all particles are actually tiny strings vibrating at different frequencies, it aims to bridge the gap between the two theories and offer a more comprehensive understanding of the universe's fundamental nature. Despite its promise, string theory is still a work in progress. It requires the existence of additional spatial dimensions beyond the familiar three, and these extra dimensions have yet to be observed. Researchers continue to explore its implications, hoping that one day it might provide the ultimate theory of everything. The journey towards a theory of everything is far from over. It is a testament to human curiosity and the relentless pursuit of knowledge. As scientists delve deeper into the mysteries of the cosmos, they inch closer to uncovering the fundamental truths that govern our reality. The quest to unify quantum mechanics and general relativity has been a major driving force in theoretical physics for decades. This pursuit is not just an academic exercise, it is a profound journey to understand the very fabric of our universe. The implications of such a unification could revolutionize our understanding of reality, potentially leading to new technologies and insights into the cosmos. These two theories, each remarkably successful in its own right, paint vastly different pictures of the universe. Quantum mechanics excels at describing the behavior of the smallest particles, while general relativity provides an elegant framework for understanding the cosmos on the largest scales. Yet they seem to operate in parallel universes, each with its own set of rules and principles. Quantum mechanics describes a world of probabilities and uncertainties, where particles can also behave like waves, and the act of observation influences the system being observed. This theory has given rise to technologies such as semiconductors and MRI machines, fundamentally changing our daily lives. The strange and counterintuitive nature of quantum mechanics challenges our classical intuitions, revealing a universe that is far more complex and mysterious than we ever imagined. General relativity, in contrast, portrays a universe governed by smooth, continuous fields, where gravity is a consequence of the curvature of space-time. This theory has been confirmed by numerous experiments and observations, from the bending of light around massive objects to the precise orbit of Mercury. It provides the foundation for our understanding of black holes, the expansion of the universe, and the behavior of galaxies. The conflict arises when we try to apply these theories to situations where both gravity and quantum effects are significant. In such extreme environments, the predictions of quantum mechanics and general relativity are incompatible, leading to paradoxes and inconsistencies. This clash is most evident in the realms of black holes and the early universe, where the forces of gravity and quantum mechanics are both incredibly strong. For example, at the singularity of a black hole, where gravity is unimaginably strong and space-time is infinitely curved, our current understanding of physics breaks down. The singularity represents a point where the known laws of physics cease to be valid, and a new, unified theory is required to describe the phenomena occurring there. This has led to intense research and speculation about the true nature of black holes and the fundamental structure of space-time. Similarly, in the very first moments after the Big Bang, when the entire universe was compressed into an infinitesimally small point, both quantum mechanics and general relativity are needed to describe the extreme conditions. The early universe was a hot, dense state where the forces of nature were unified, and understanding this epoch could provide crucial insights into the origin and evolution of the cosmos. String theory attempts to bridge this divide by proposing a radical new framework for understanding the fundamental nature of reality. It suggests that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can exist in multiple dimensions, and their vibrations determine the properties of particles and forces. It suggests that at the most fundamental level, the universe is not made up of point-like particles, but rather of tiny, one-dimensional strings. These strings can vibrate at different frequencies, and these vibrations give rise to the different particles and forces that we observe in the universe. This elegant framework has the potential to unify all the fundamental forces of nature, including gravity, into a single, coherent theory. These strings can vibrate at different frequencies, and these vibrations give rise to the different particles and forces that we observe in the universe. By providing a common foundation for both quantum mechanics and general relativity, string theory offers a promising path towards a unified theory of everything. However, it remains a highly speculative and mathematically complex theory, and much work remains to be done to test its predictions and fully understand its implications.